Start? Yeah. Okay, so thank you very much. First of all, thanks to the organizers for the invitation. Very special place and pleasure being here. So I never met Lakshmibai in person. However, she had papers on, if I write it, toric degenerations. Of Grassmannians. And also flag varieties in more general settings. And these papers were very influential on the field. So there are some papers in mathematical physics influenced by that. And of course, for mathematicians, they were very important because the kind of general idea for the whole my lectures is like that we have Lie theory. And in Lie theory, we have different parts. So we have algebraic part. And then, of course, we have geometric part. And combinatorial part. Of course, many more parts. But so it's not only the Lie theory, but there are many kind of connections and links and outcomes, applications. So it means that there is a large outer world which had to do with the Lie theory, and the direction is in both, so important for both kind of sides. So from one hand, you can use the machinery of the Lie theory, well developed, well studied. We have now many things here to study some seemingly unrelated objects outside. However, there is a life outside, which is also can be seen here. We don't see some structures, but we do, if just looking here, but we do see them looking out. So this is the general idea, and this is what I'm going to talk about this week. So let me give plan. So the general plan. So today I'll start with the kind of classical notions, classical theory. So the goal for today is how to fix notation and just to describe the objects we're going to work with in a very, very classical and standard thing, but still we need all those to combine together to move further. Then I'll make a first step outside. So this is what is called sometimes PBW, or abelian version. So this looks very innocent. So in the sense that you start with the Lie theory with some classical structures, you do something, and then it turns out that there is there are many new directions, new connections, and so on. So we'll see that. Then I'll go further to describe the, let me say, families and Quivers. So these objects, they have some Quiver part or Quiver flavor, and we'll discuss this in more details. In particular, we'll study some families of flag type varieties, and we'll see that they are kind of similar to what we already know. So then I'll pass to the cyclic to the cyclicity or cyclic Quivers. and together with Grassmannians. And then finally, I'll try to say something about affine like varieties and Grassmannians. So actually, I'm afraid that this program is a bit too optimistic. Maybe I'll not be able to get here, or at least I'll be able to say in a few words, but I'll try. And before I start, let me maybe put some names here. So this is very classical. This second part is based on some joint works with Gislan Fourier. Peter Littelmann. So this is also based on joint work also with Xin Fang. Gislan Fourier. Giovanni Cerulli-Relli. Markus Reinecke. And this part is partially based on joint work with Martino Lanini. And Alex Putz. Okay, so also this is a kind of outcome of the previous thing. And maybe before I start, so let me say that it's a special pleasure talking here because there are many Indian mathematicians who worked and still work in the field, and their contribution is really crucial and very, very important. Okay, so this is the general plan, and now let me give a plan for today. So I'll start with just some very general notation. From the Lie theory side, Lie algebras, Lie groups, just to have things here settled. And then I'll say something about representations. So if you wish, this is going to be an algebraic part or representation theoretic part. And then I'll go to geometry, Grassmannians, like varieties, Schubert varieties. And finally, I'll say something about, well, combinatorial side, background. So these are Lucre algebras. And standard, semi-standard tablet. So this is the plan for today. Again, maybe a bit too optimistic, but we'll see. So the goal is to somehow settle, as I said, settle notation. Yes, and maybe one more thing before I start. So you are very welcome, of course, to ask questions at any point. So please just interrupt. Good. So let us start. So we have our, so G is a simple Lie algebra. So actually for the whole week, I'm going to work with SLN. So we can assume from the very beginning that it's just a special linear Lie algebra. Sometimes we'll need GLN, but not more. So, but the important and interesting thing that most of the constructions, they do work in much larger generality, but for us, for the whole week, it's going to be just SLN. So, so we have a standard decomposition, SLN into n minus h and n. So this is the Lie algebra of strictly lower triangular matrices. So these are traceless diagonal matrices. And these are upper triangular. And also, it's convenient to introduce the Borel subalgebras. So we say that B minus is n minus plus h, and B is n plus h. Okay. So, well, of course, there is a standard basis. Standard basis for all of them. So we do have, so since these are trace of matrices, we do have our matrix units forming basis of that. However, let us introduce just maybe more theoretic notation. For that, we'll need the notion of roots. So let phi be phi plus and phi minus. So these are all roots. And positive, negative parts. So this is a subset in H star. Yep. Yeah. Point. So maybe I write it at the very beginning. So our base field is E. And maybe at some point we'll need to be here. Here we'll need some real structures, but maybe even so everything is some. Okay. So we have alpha 1, alpha n minus 1. These are simple roots. And all the roots are just sums of those. So let me denote by alpha ij, the sum alpha I plus alpha j, with 1 less than or equal to I j most n minus 1. So these are all possible positive roots. All positive roots. And let us denote by Fij and Eij the corresponding basis elements. So F alpha ij or simply Fij. So these are elements in n minus. So these are corresponding elements in the Lie algebra. So we can write it explicitly. Well, maybe also I write E alpha ij, which is Eij. These are elements in n plus. So maybe to be precise, I should have written here minus alpha ij, but just to, anyway, I'm going to use this shorthand notation Fij, so we don't. And say, for example, so Fij is Ej plus 1i. So these are just a matrix unit. well, and these elements form bases for our. Okay, so we will also need HIs, which are elements in H, again, very explicitly written as EII minus E plus 1. So these are our, so we have HIs, Fij, and Eij, the form basis of S. So probably, right, so that's probably it I wanted to say about the Lie algebra. So let me also fix the notation for the Lie group. So this is the determinant, so Lie group of matrices with determinant 1. So this is the Lie group of the Lie algebra SLN, again, complex. And we do have inside the Cartan subgroup. So this is the Cartan subgroup of diagonal matrices. And we also have the unipotent subgroups N and N minus. So these are Lie groups corresponding to N and N. Okay, and finally, I'll also need Borel subgroups. So B and B minus. These are upper and lower triangular Borel subgroups. So let me repeat that for us, our group G is SLN, so they have very concrete realization. In general, of course, they are all well defined for any G. However, they're not that explicitly. Okay, so probably that's it about the standard SLN notation. So let me get forward to the representation theory. So first of all, we have a very well-studied class of highest irreducible finite dimensional highest weight representations, G modules. So they are labeled by integral dominant weights. So we have the set P. Yeah, maybe I should introduce. So let omega I from 1 to n minus 1 be the fundamental weights. So we know that omega I of Hj is delta Ij, or this can be written as via the standard killing form. This is delta Ij, so for the killing form. So in principle, one should put here check, but for us, SLN is SLN, G is SLN, so we don't care. Okay, so now P is the set of integral weights. So this is direct sum Z omega I from 1 to n minus 1. So we take the lattice spanned by our fundamental weights, and inside we have P plus inside P. So this what is called integral dominant weights. So P is the direct sum of from I1 to n minus 1, Z greater than 0 omega I. So in other words, any element here is given by the sum I from 1 to n minus 1 mi I. This is an element in P plus where mi's are non-negative. Okay, so this is our lambda. So we can either use the shorthand notation lambda, or we can denote this lambda by a tuple of mi's. These are just coefficients of the decomposition of lambda into the basis of omega. Okay, so for each such a lambda, we have v lambda. So this is irreducible highest weight SLN module. So in particular, we have a highest weight vector, v lambda inside, and the whole space is obtained by applying the universal enveloping algebra of n minus to this highest weight vector. Okay. So probably the most is just m times omega. So there is a single omega here, and the corresponding representation v m omega is just you take your vector v m omega and you act by f. So there is a single f here for SL2, and then you do so many times until you get to f to the m v m omega, and after that f goes to 0. So here the dimension v m omega is m plus 1. Okay, so this is for SL2. In general, we do have, of course, dimension and character formula. For example, the dimension of v lambda is the product over 1 less or equal to I, j, and less or equal to n minus 1. And we have here mi plus mj plus j minus I plus 1 over j minus I plus 1. So this is just a very concrete formula. Again, we're not going to need it, but still, I just wanted to say that this is something very, very well studied, very, very well known. Okay, so also maybe it's good to have the notation for the characters. So the characters of v lambda is just formally defined by the sum over all mu in H star, z to the mu, and then dimension of v lambda upper mu. So here this v lambda mu is just the space of v in v lambda such that h times v is mu of h times v for any h in. Okay, so this is just the space of weight mu vectors, and z to the mu is just the formal component. By the way, maybe let me add it explicitly here that I wrote that the whole space is generated by the action of n minus. However, there are, of course, two other properties that if you apply n plus to v lambda, you get 0, and v lambda itself spans, it lives in v lambda lambda. So this is the weight lambda vector, and it spans this weight. Okay. Sorry? Absolutely, right. So this, actually, to be precise, is omega 1, but still for SL2, we have only one omega. Sometimes this omega 1 is denoted just by. So you mean for other than SLN, or for not for SL2? No, for, you see here in general. So maybe let me answer. So in general, the omega, if you take just omega 1 itself, then the corresponding representation is just a vector representation of SLN. So it's just of dimension n plus 1. So for example, for SL2, this of dimension 2, for SL3 of dimension 3, and so on. And then if you take m omega 1, this is going to be symmetric power of this fundamental of this vector representation. So it's some binomial coefficient, but also very, very explicit. There are several ways, and then I'll get there. Yeah. Let me maybe give several examples which are going to be very, very important for us. So actually, I've already started that. So examples. So if we have SLN and lambda being just omega 1, then V lambda is just C to Vn. So this is vector representation. Okay, so just the n-dimensional vector space where matrices act as matrices. And then if we have lambda being m omega 1, then V lambda is the mth symmetric power. V. This doesn't hold, of course, in general for any weight. If you scale it, you're not going to get the symmetric power, but it works here. And then another very important example is fundamental weights, which are different from omega 1s. So again, n is arbitrary, then V omega k is the kth Birch power of V omega 1. So this is going to be a fundamental example for us for geometry, for combinatorics. So these are examples. Maybe one more example that so if lambda is omega 1 plus omega n minus 1, then what you get is just the adjoint representation. So these are the kind of standard examples. So now let me add the last thing here. So we'll need the while group. So let me fix the notation also. So the while group. W for SLN is just a symmetric group. So in general, and here as well, it's generated by simple reflections, I from 1 to n minus 1, so simple reflections. Okay, so in general, you just have to multiply those SIs, and you get something which in this case is just a sense. So what's going to be important for us is that W just by definition acts on the space of weights, on the space H star. And important observation is that the dimension V lambda mu is equal to the dimension of V lambda W of mu for any W in tau. So it means that the dimensions of, so the group acts on the weight, so I can apply W to mu, and then I can look at the spaces mu, weight spaces mu, and weight spaces W of mu, and they are in a sense isomorphic. This is the claim. And in particular, the most important thing for us is that the corollary is that the dimension of V lambda W lambda is 1 for any W in W, and we denote by V W of lambda some fixed vectors there. So V W of Okay, so this is the some subspace in our representation space, and it has dimension 1. Let's just fix some vectors there, and these are called extremal weight vectors. So why do we care? Because let's finish with this part with the following definition. So the de-Mazur modules. So they are denoted by dw lambda. So we have two ingredients here, the wild group element and lambda, which is the highest weight of our representation. So this is a subspace inside V lambda, and you take your B and you apply it to the extremal vector W. Okay. So you please note that B is that B which fixes the highest weight vector. So in particular, example, so if you take D E lambda, so where E is the identity element in our while group, so we act by B on V lambda itself. We're not getting anything U, so this is just span of V lambda itself, just a one-dimensional space. However, if W0 is the longest element in the while group, then W0 lambda is the whole thing. So because B generates everything from the lowest weight. Okay. Good. So probably that's it. Any questions? Span of V lambda. Here, it's span of VW lambda. So we take some vector which spans this space, and we denote it by VW. More questions? Okay, so then let's go to the geometry. And here is going to be maybe a bit less familiar because, so there are actually several ways to look at flag varieties. And in type A, there are even more. So let me use the following definition, which is not kind of very, very standard, but it's going to be important for us. So we take lambda in P plus. And representation. So the group SLN also acts on V lambda. And we are going to somehow consider the action of P on the projectivization of V lambda. So this is projective space with the underlying vector space being our representation V lambda. Okay? So just the space of all lines in V lambda. And of course, we have an action. So it meets an action of the group SLN, right? Because so if the group acts on the vector space, you can just extend or induce the action on the space of lines. And inside, we have a very special line, which is just the span of V lambda. So this is C times V lambda. So it's just a point in the projective space. Okay? And now here comes the definition. Which says that we take F lambda. So this is a variety which so far at the moment depends on the weight lambda. Maybe let me, yes, I have it here. So lambda is from P plus, and this is just the, so what we do, we take the Borel subgroup, B minus, and apply it to the point V lambda. So this is happening inside the projective space. And then we take the closure. Okay, so let me say in words. So what we do, we take the highest weight line and apply to it b lambda and take this one. So actually, maybe let me write once right now. So remark saying that actually you can say that f lambda is the same as n minus applied to v lambda in the closure. Or if you don't like the closures, you can take the whole G and apply it to V lambda, and then it's already closed and you don't have to do. However, there are many situations where this definition is better than this one, because in particular for some more complicated G's, so not simples, of course, this might be non-closed as well. So in a sense, for us, this is going to be more conceptual. Okay. So again, the basic example here is SL2. So then we can take V lambda, which is just m omega 1, so it's still there. And what is our B minus is actually a very simple group. Actually, we can work with that. So B minus has diagonal part, which does nothing with the line, right? It just stabilizes it. So this n minus is just the set of matrices of the form 1, 1, whatever, 0. Okay. And then we take our projective space. Actually, we have a picture here. So we have this picture, and then our group is the exponent of this F. And you just take point inside the large projective space, and you start applying exponents of this operator, right? So this is nothing but what is called the Veronese curve. So F lambda is actually isomorphic to P1. And this is the Veronese curve in PM, right? So this PM is P of Vm omega 1. So here the dimension of this space is m plus 1. Therefore, what we get is m-dimensional projective space. Okay? So please note that in principle, we started with an arbitrary m, but the result is a variety, is an algebraic variety, does not depend on m. Well, the embedding doesn't depend, right? So these are different embeddings of the same projective space. However, what we get is just the same thing. And then the reason is very simple, because so we get another realization. So this remark saying that this F lambda is actually G over P lambda, where P lambda is a stabilizer of G. Okay, so we've seen that this is the orbit. So therefore, in order to get the orbit, you factorize by the stabilizer of your point. And it's very easy to see here that the stabilizer is just the Borel subgroup, right? Maybe I write it explicitly. So for n equals 2 and any lambda, one has that P lambda is just the Borel subgroup, which is just a set of matrices of the form kind of opposite to that. Yeah. Absolutely. Absolutely. We first take, yeah, maybe it's a good point. So to say that, so Veronese curve, so provided M is pi. So we actually, it's a good remark that we have actually two cases. So one case is M is 0, and then we just get a point, right? So nothing happens. And another case is we get the P1. We'll see it in more general settings, but this is how it works. So let us maybe consider one more very special example, but again very important. Good. Yes, otherwise, so if lambda is 0, then this point is stabilized by the whole group, and so we quotient just by the group. Okay, so this is, so since we've written this, so the conclusion, the outcome is that, right. So the outcome is that, so if E lambda equals P mu, equivalent to F lambda equals F mu, and actually we see from here that this is equivalent to saying that supports of lambda and mu coincide, where the support of some mi omega I from 1 to n minus 1, just a set of such i's that mi is strictly positive. Okay, and this is exactly actually the case we've seen there, right? So the support for SL2 case can be either trivial, empty, or just being the whole thing, because we have only one element, and therefore these are two different cases. So in general, we just have to say what are the non-zero ingredients, so what are the non-zero fundamental weights which enter into the decomposition of lambda into the sum of fundamental weights, and then this is this. So therefore, it makes sense to consider the simplest possible situation. So let's work out an example. The example of n is arbitrary, and lambda is omega k. So k is from 1 to n minus 1. So we've seen actually that it's not important we take either omega k or multiple of omega k, but let's do omega k itself. And we can ask what is f omega k. At least what we know is that this sits inside the projective space of v omega k, right? So by the very definition, so we should start with the fundamental representation with the weight exactly lambda. And this is nothing but p of lambda k of v omega 1, which is just the fundamental vector representation. And actually, this is nothing but the celebrated Lucre embedding of the Grassmannian. So let me give the answer in this example. So more precisely, f omega k is nothing but the Grassmannian k of v omega 1. So this v omega 1 again is just the n-dimensional space. Well, one can see it in various ways. For example, so let us also fix this. So let v1 up to vn be the standard basis of our v omega 1. Then the highest weight vector v omega k is just the Verge product of the first k basis vectors, and therefore our v omega k is just the span of this v1. Okay, so this is how it works, and then you can check that we have the Grassmannian is indeed generated from this vector by the action, but this is very standard. So maybe let me add one more thing here, since again this is going to be important tomorrow. So the stabilizer of this vector, or this line rather, V omega k is what is called the parabolic subgroup, which is just the maximal parabolic. This have zeros here, and then everything else here. So here you have a element, and so also k here. So this guy is maybe. This guy is k times n minus the zero part. Okay, so this is one example, and another example is if lambda is omega 1 plus omega n minus 1. Sometimes this is denoted by rho, which is the sum of all fundamental weights. So the support here is the maximal possible. So this is the case of the support being the whole set of indices, the whole set of roots, simple roots, fundamental weights, rather. Then we know that f lambda sits in P of V lambda. And actually, which is V rho here. And actually, it's a question how to describe this. And the answer is well known. So let me state the answer, and then I'll give one more structure, and we'll see that it's actually related. So in this case, this is the collection of spaces V1 in V2 in Vn minus 1, such that V sub k is an element in the Grassmannian k v omega 1. Okay, so this is chains. These are chains of embedded vector spaces. The dimensions are 1 to n minus 1. And so we see that actually this has to do with, this description has to do with Grassmannians. So the elements there are actually element points in the Grassmannians. And important thing here is the following Cartan, again, very well known, Cartan embedding. So this is the observation saying that for any lambda mu in P plus, V lambda plus mu sits inside the tensor product of V lambda tensor V mu. Sometimes this is called the Cartan component of the decomposition of the tensor product. So more precisely, this embedding is very, very explicit. It says that suppose we take vector V lambda plus mu. So this is the high state vector of a representation corresponding to the sum of lambda plus mu. And then if we map it to the tensor product V lambda tensor V mu, then we get embedding of modules. So it means that you take some, so this is embedding of G module. Right, so it means that the module V lambda plus mu can be realized inside the tensor product of V lambda tensor V mu in a very simple way. Just take the tensor product of two high-state vectors, and then we apply the universal enveloping algebra of n minus. So in other words, V lambda plus mu is realized as universal enveloping algebra of n minus applied to the tensor product of vectors. And this fits inside V lambda tensor. Okay. Here, because we have the following corollary saying that F lambda plus mu sits inside F lambda times F mu. Right, and this is just again, what we have to do is, so the point, the line now V lambda plus mu is mapped to V lambda times V min. Right, and actually, this guy lives inside P of V lambda times P of V min. Okay, so what is the idea? So in principle, F lambda plus mu is a subvariety inside some very large space. Well, could be large. V lambda plus mu. However, it makes sense to, well, from one hand, to make the picture more complicated, instead of considering one projective space, consider the product of two. However, these guys are smaller. We'll see it in a minute. And therefore, you are working with a larger number of projective spaces. This is a price to pay, but what is the kind of benefit? The benefit is that those projective spaces, they become much. So let's see how it works in our situation. In our situation, we have the maximal flag variety, which is the flag variety corresponding to the support, the full support. And actually, maybe I should add here in this description that this is the linear algebra description. However, we also have description that this guy is G mod B, and probably this is the most familiar definition. So you take the Borel subgroup. This is exactly the subgroup which stabilizes a high state vector for lambda with the maximal possible support. B is just the Lie group of upper triangular matrices. And then this G mod B is exactly the flag variety for G, the complete flag variety, the largest possible. However, we see that, the conclusion is that G mod B sits inside G mod B1 up to G mod Bn minus 1. Simply because V omega 1 plus omega n minus 1 sits inside the V omega 1 tensor V omega n minus 1. Okay, and actually, so each G mod Pk is actually Grassmannian. And we see that our linear algebra description somehow agrees with that. So our variety sits inside the product of Grassmannian. The non-trivial question is, how does it sit there? And the answer is that it's just the chains of subspaces which are embedded into each other. Okay? Probably that's it about the general thing, but maybe one more important thing to say is to define the Schubert varieties. Schubert varieties. So this is the important class of subvarieties. Let me denote them by X, W, lambda. So again, as in the case of De Mazur modules, we have a Weil group element and highest integral dominant weight. And this is defined by saying that you take B and you apply it to V W lambda, then you close, and then it sits inside the projectization of De Mazur module, or you can see it inside the projective space of V lambda. And actually, it also sits inside F. So let me say in words, what do we do here? We take De Mazur submodule inside highest weight representation, and it has this extremal weight vector. So you remember for any W, an element from the Weil group, and any lambda, we defined these extremal vectors spanning the extremal weight spaces. And then we have our upper triangular B, which is just explicitly given subgroup, and we apply it to here, right? We get something. This something lives inside our projective space, either small projective space, a large projective space, or inside F lambda. So let me give you examples. Again, the two favored examples are, so if W is just E. So then this X E lambda is just a point, which is just a point V lambda itself, right? Because B stabilizes this point, and you're not getting anything else. However, if W is W0, then X W0 lambda is just the whole thing. Good. So I have another 3 minutes. So let me spend these minutes on saying something about the combinatorial part. Maybe I'm not getting there, but at least what do we want? What's the goal? So, sorry? Where? Gmod, yes. F. So in the case lambda is the row, the sum. Okay, so we saw that our flag variety. So suppose from now on I denote by Fn the flag variety for SLN. So again, let me write that Fn lives inside the product of Grassmannians and just consists of collections n-1 spaces. So since it lives in the product of Grassmannians, we also get the embedding into, so let me rewrite it. So Grassmannian K V on 1. Then sits in the product of Grassmannian K V omega 1, K from 1 to n-1, and this lives in the product of projective spaces, lambda K 1. Okay, so these are projective spaces, projectivizations of the Verge powers. And then we can ask, how does it sit here? So it means that we have variety sitting inside the product of projective spaces. We can ask, what is the image there? So how to describe it? And for that, so let's, as before, so V1, V, and the basis of V omega 1. Then we can form, we take I to be a collection, I1 to Ik. So these are numbers from 1 to n. They can form vector V sub I, which is just the Verge product of Vi1, Verge Vi. Okay, so these are vectors from the Verge space, and then we can take the dual elements, so delta I. These are dual to Vi, and these are called Plücker coordinates. So the question is how to describe the vanishing ideal, or how to describe the embedding, how to describe the image in terms of these Plücker coordinates. So these are coordinates on these projective spaces. So we have coordinates on the product of projective spaces. So how to do that? And the Plücker algebra is actually the answer. It's also called the homogeneous coordinate ring. So this is the quotient of the polynomial ring in on all these I, delta I, by the vanishing ideal. So this is the vanishing. Okay, so let me stop here, and then tomorrow we'll start with finishing this part, just saying what is the Plücker algebra, how to describe it, and why do semi-standard tableau play a role here, and then we'll move further. with more kind of